Hey, so good afternoon, everybody. Do you have any questions before we start? Uh, I figure I will go over homework number 2 with you first, real quickly, just a few minutes to, explain the motivation and give you some ideas what I'm looking for. Even though there are multiple pages in this problem set, it's actually pretty straightforward. You understand the basic ideas of neural network. We're talking about classical neural network or artificial neural network, right? So what you need to familiar yourself with is the vector notation, frankly speaking. I'm trying to use some very simple neural network, two layers, two-layer network that help you kind of sink in the idea of using vector to represent the weights, the activation vectors. So with that in mind, the first problem really is just to ask you to prove using an example. Use an example to prove if there's no activation function, meaning your activation function is essentially a linear function, then your output will just be essentially a linear combination of the inputs. That means you don't actually get any nonlinearity out of the data set. As the data set gets more and more complicated, there are nonlinearity inherent to this. Find out that pattern. So this is to prove that point. Okay. That I kind of mentioned at the beginning that why activation function, especially the nonlinear activation functions, is critical in the whole neural network operation. So I don't want you to prove general cases. I give you a very simple, full neural network, two-layer. I even label all the weights for you. So get familiar with all those weights. What does that really mean? Superscript. Right? What does that superscript mean? What does that subscript mean? And I have biases for each layer. And your job is to prove that the output y hat is essentially a linear combination of x1 and x2. Yeah.
The weights of after the second there's the weights there. So that example is that how it's structured. Because for the first weights you have 1, 2, and then for the second one you have like 2, 1. Go down to the next one. So
You mean this one? This length?
yeah, like for x2 for the weights, you have 1, 2. That means like the 2 is for the x, right? And 1 is for the threshold.
Right.
Then looking to the
So
second.
the way you read the subscript is that if this one is reversed.
Yeah, I was thinking, is it reverse or is that how it's structured?
Give you a second. Okay, so the way we structure the index, the subscript is that the destination is actually in the front, and the source is the second one. So this makes sense, right?
The second weights, the destination is the first one, and the source is the second one.
Yeah. So destination is the second one, the first one, right?
And for the second weight,
Destination, the one, this one.
yeah,
Destination is one. Yeah, you're right. This one should be 1, 2, and 1, 3. Yeah, I'll revisit and make sure that we unify the notation. Good catch. So this one is pretty straightforward. You just follow the instruction. I even give you step-by-step instructions. Follow. Okay. All right. The second question is to expand on your understanding of classification. universal classifier. And just use very simple example to derive a decision boundary. So in this case, we have a very simple 4 points data set. So obviously you know how to draw the boundary, right? Anything that separates the blues from the blue points from the red points. But I want you to use a neural network to represent it. To use a one neuron network to and identify what's W1 and W2. Well, actually, I give it to you already. I even give you the bias. So you use those numbers to derive a decision boundary. It's pretty much a linear function, right? So that's a simple exercise. But the second one is getting the part B is getting a little bit more interesting. I want you to prove a very basic. Actually, this is when problem happens with the original single perceptron. When they realize the single perceptron cannot implement an exclusive OR. Right? And that's when we started to use multiple perceptrons to implement a logic function such as exclusive OR. So this part B is to use a simple, 3 neuron, two-layer network to derive a proper decision boundary for exclusive OR. So we all know what is a one, what are ones for exclusive OR? If the input, so exclusive OR is one, those are the blue ones. Are one, if either one of them is one. If the x1 and x2 are the same, then they are zero. That's exclusive OR. So the decision boundary for this, we know what it is. I want you to use this neural network to write that. And you can assume the the activation function being signal. What's interesting after this is I want you to take a look at each neuron and kind of dig into the output of each neuron and have have kind of a truth table for each neuron. So you can think about this as a truth table of the first neuron. After the first neuron, what are the outputs? After the second neuron, what are the outputs? Then you combine them together, you find out what's the output of the truth table of the final neuron. And you should verify that this is an exclusive OR. So that's consistent with the notion that I want you to understand. I have a feeling that what each neuron is doing individually. What are they classified? And when you combine them together, are they doing exactly what you want? That's this exercise.
Do you want us to write it down on the paper or like?
You mean this whole exercise? You can type it up or you can write it. That was your question?
Yeah.
Yeah. No, I don't want you to type it if that takes too much time, but you need to write it really neat so I can understand what you're writing.
You define what deeply means actually.
You're writing a 3. If you're writing a 6, I don't want to confuse it with a 4. Right? That's a very obvious example. So if you
Oh, my handwriting's not that bad.
I'm pretty sure yours is good. But try your best. Okay, don't let me guess what you're trying to write. Okay, otherwise I will return it to you. Okay, I'm not gonna I'm not gonna give you a bad grade just simply because I couldn't understand what you're writing. I will return it. Do it again. But I will be a little bit upset if your handwriting is bad. Okay.
Um, so then just kind of repeat the analysis for decision boundary, okay, on this exclusive OR. Okay, if you have if you have part B done correctly, then you should be able to write this pretty quickly. Do this very quickly. Okay. Third problem is the easiest one. I only want you to kind of exercise the whole propagation using the vector notation. Okay. Go back to the first problem. You use vector notation. Calculate full propagation. Okay. The last one is probably the most interesting one. We have played around with this TensorFlow playground, right? There are different. Let's see if I can pop this one out. Okay, remember this one, right? So I want you to experiment on the spiral data set. So this one. Go on the corner. Spiral. And just started to experimenting on different numbers of hidden layers. You can go crazy, but I want you to kind of get started with something simple so you can compare. You start with one hidden layer, just a few neurons. The things that I need you to play around is really the activation function. So if you look at the activation function, the pull down menu, they have a few choices that we cover, right? So play around with it and see how things converge. How do you see the convergence or non-convergence? Is to look at the output right? On the right-hand side. If you start to see classification, you start to see boundary between the blue points and orange points. That usually also reflected on the output where they say test loss and training loss. I'm not going, we are going to see those terms in the future, but when you see they draw a diagram, you pretty much know right away whether you have a good convergence, right? And loss, that's exactly what we talk about in loss function. The loss, it means loss function, means your residual error. So if you are approaching zero, that means you have good convergence. You're probably going to see a very clear classification between blue and orange. So I expect you to run some experiments, just play with it, play with different activation function, take snapshot, change the parameters for hidden layers, change the length, change the depth, change the width, take snapshots, and make some observations. So it's all in the instruction. Right, so that's homework number 2. That make sense? Hey, let's get back. All right. So last time we started to talk about the gradient descent. So can you describe gradient descent? What is gradient descent? What is gradient descent for?
Convergence.
Converging for what? Very good. So you'll start with the definition of a loss function. So what is a loss function? Simple. Simple explanation. What is a loss function? A cost function. Right. So it's the residual errors, right, between the desired output, which is your y, and the estimated output. Right. And we usually put a nominal distance notation around it. So that's actually your cost function. So the other thing that we talk about is exactly what are we learning in a neural network? What are we trying to achieve? when we talk about this learning process, exactly what are we learning? We learn to minimize the cost function, right? But the cost function has manifests itself in the parameter of weights, right? Because your output is essentially a function of the input and the weights. When I say weights, it also includes biases. So our job is to find out the optimal weights and biases that minimize the cost function. So when the cost function goes down consistently, you know you are on the right track. So if cost function kind of zigzagging, divergent, and you have done something wrong. Our job is pretty simple: is to optimize find the minimum of the cost function by finding the optimal weights. That's the basic definition. Okay, so then what are the typical cost functions? The one that we are most interested in, and we use a lot of example, is to use the classical classification metric, not metric, the cost function, which is the log loss function. We'll see a lot of log loss today. So now we have to ask ourselves, all right, so I know the big picture now. How do we actually calculate or implement gradient descent? There are two steps. We'll see a big picture pretty quickly. There are two steps. First step is to perform forward propagation from the input to the network output, from X to Y. That's called forward propagation. But in order to perform gradient descent and update the weights, we do a very important technique called back propagation. So basically, you are going to use both forward and backward propagation to calculate gradient descent. And this is an iterative process. But before that, I want to kind of, by the way, this is probably as mathematical as much mathematics that I have for this semester. Okay? This is probably the most math that we will cover throughout the semester. And it's actually pretty simple. Okay? You just need some refresher. So I want to talk about loss function first. I want to talk about the specific, to be specific, I want to talk about the log loss function. Okay. So we have seen this slide last time. Let's stop here. The log loss function is defined as the difference, obviously defined as the difference between your desired output and your estimated output. But instead of using a linear combination, we use a log function. The log function really is a natural log function, not the log 10 function. So that is the one on top is a loss function for one sample, meaning x1, x2, x3, for example, those input, you only have one of them. We know your data set has a lot of data. So let's say we have m samples. Then your complete log function, loss function is defined by averaging over a number of samples. And you add all the loss functions for each individual sample together, right? And you average out. That's your loss function for the whole sequence or for the whole data set. Okay. So if your data set has 1,000 samples, you actually pass the whole data set one sample at a time through the network. You pass all, and that's one epoch. And back propagation is just, I have to have a definition here, but back propagation use something that you have done in calculus. This chain rule. Calculate the gradients. Calculate the gradients. So back propagation is designed to calculate the gradient. Okay. And back is the reason we call it back propagation is because it actually started calculating the gradient from the output and trace back to the input. So it's backward from the output layer to the input layer. And we'll see why very quickly. Okay, this is the big picture. I want you to take this, remember this. This is the basic idea. I use a very simple two-layer neural network as an example with three inputs, x1, x2, and x3. So 4 neurons in layer 1 and 1 neuron in the output layer. In the top half, we call this forward path or forward propagation. And that's pretty much calculating the network output starting from the input. And each of the box represent a calculation. So I think by now you should know Z1. What is Z1, right? What is Z1? So Z1 is it's associated with the first neuron, the neuron in layer 1. So right now, I also want you to get used to the idea that each one of those notations are actually representing a vector. A vector representing every Z in layer 1, the first layer. W1 here is every weight vector in first layer. Same thing with B1, all the biases in the first layer. Okay, so when you look at the equation, it's no longer just a scalar, it's actually a vector representation. Okay. So the first two boxes, the first two blocks represent the neuron operations for the first layer. First part is to calculate Z, second part is to do an activation function, right? And the third and fourth blocks are for the second layer. Very much similar to the first two blocks, just repeating it, changing the superscript for layer 2. And you eventually get the output, which is the activation function, the activation output of the second layer, right? Right now, the lower part, gradient descent to find optimal weights, is a black box. That's something we will open today, okay? But what's the connection between those two? Between forward propagation and the back propagation? There's a function that connects those two. The loss function, right? You calculate the loss function when at the end of the forward propagation. Because right now you know the expected output and the estimated output. So you calculate the loss function. And you feed that loss function into that propagation chain to update the weights. W1, W2, B1. So that's essentially a high level operations for any neural network. Forward and back propagations. Okay. Still, I want to kind of build some foundation before we move to the algorithm itself. I want you to look at the log loss function in a little bit more details. It's okay, used to looking at this. So if you break it down, there are two parts of the log loss function. This is kind of symmetrical, right? The way you read it is the first part, y multiplied by log AL, is associated with the case when y equals to 1. Remember, this is for binary classification. So your y, the output can be either 0 or 1. Therefore, the second part, 1 minus 1 multiplied by log 1 minus AL, is associated with y equal to 0, right? In this case, we also assume that the activation function is sigma. The sigma activation function. Right, so the next bullet points really just tell you how you read this. When y equal to 1, the loss function reduced to a single term. Basically the first term, right? Minus log AL. Does that make sense? Right? Because there's no second term. Oh, y equal to 1, the second term is 0. Right? We only have this one. The first term. If y equal to 0, the first term vanished. You only have the first term, right? This y equal to 0. So essentially you have minus log 1 minus AL. Okay. So that's the way you look at this loss function. They only exist, only one term exists in any condition of y. Okay. So with that in mind, it's not hard to see that loss function is always positive. Do you agree? It's always positive. It has to be always positive because the definition of a cost function is the distance between two vectors. And the distance has always to be positive. But the way that they define a log loss function, now I just want you to make sure that you can prove that it is always positive. Why? If you look at this, let's just look at log x. Just look at the first term, log. This first term, minus log AL. Why is minus log AL always positive? This AL is the activation output. Then what is the activation output for sigma? It's always between 0 and 1, right? It cannot be exceeding 1. It cannot be less than 0. That's the sigma function. Always be constrained between 0 to 1. So tell me what's the log of 0 to 1? The positive number or negative number? The log. This is simple algebra. Okay, please. If x is not greater than 1, log x is less than 0, right? If x is less than 1. Of course, x cannot be less than 0. It cannot even be 0, right? And that's exactly what sigma will give it to you. All the numbers are constrained between 0 and 1. But they are never 0. They can be as close as to 0 or as close as to 1, but they are never 0 or 1. Does this make sense? Log. What is the log going 1? Has to be a minus, a negative. So if you do it 1 minus AL, it's the same thing. If AL is between 0 to 1, 1 minus AL is also between 0 to 1. Then that's also a negative number within log. And you take minus sign of that, then it's positive. So it's good. We know log loss function is a good candidate, at least from the magnitude standpoint, always positive. And we want our loss function to be positive. That's good. So if you look at, you guys can go back and plot what's log x. That's log x with a minus sign.
the loss function approaches zero when your x is approaching 1. So this 0, so when log function, when the loss function approaches 0, which that means you are giving up to prediction, right? Okay, because your loss function is really small. If you look at the other way, when y equal to 0, to do it the other way around, when loss function is close to 0, it's actually a very small number, small z. That small z will turn the loss function into a very small number. Okay. If you look at those two charts, they actually kind of have a minimum. They are both convex upward, but they do have a minimum. So why do we like this? Because we want a minimum. In gradient descent, our job is to find a potential minimum. So log loss function has that feature or property to allow you to find a minimum cost function. Okay. So that's one thing I want to mention. The other thing I want to mention is pretty important too. Is differentiability. So mathematics, what is differentiability? What does that mean?
Wait, second.
That first word.
Oh, differentiability, but they're the one,
It's, derived.
the derivatives exist.
Derivative exists. Exactly. That means you can take a derivative of that particular function. Right? I mean, isn't that important? Of course, it's important. Otherwise, our whole base of updating the gradient will not work. You run into a gradient function that couldn't do differentiation. So that's something that we have to pay attention as well. Okay. So this means that the loss function has to be differentiable with respect to the weights and the biases. Then I want to take it one step further. I also say, very important that your activation function also needs to be differentiable. But why? That's because this is, I'm using this as the example. That's because, one sentence, that's because your loss function depends on activation function. It's a function of the activation function, right? Because in the forward propagation, you go through different stages of neurons. There are activation functions associated. So your loss function really at the end depends on the previous operations in terms of activation function. So that kind of chain reaction dictate that your activation function needs to be differentiable as well. But if we just use math, at the end of the day, I want you to use math to prove that. Pretty simple. Okay. Just to look at the middle, we want to calculate the gradients of W2 and W2 and B2. Okay. So if you use the chain rule in the middle, the partial derivative of J with respect to W2 can be represented by this chain rule. Partial derivative of A1 multiplied by partial derivative of A2 with respect to W2. Do we agree? This first equation is the chain rule. Right? Tell me you don't understand if you raise your hand if you don't understand. Good, right? You can cancel out partial A2. You will get partial J, partial W2. Let's just change it. If you continue, partial J, partial A2 multiplied by that final equation, why is that one valid? Because A2, yeah, A2 is the output of the activation function.
Right, so that's you. So this last term is the derivative of activation function with respect to W2. And since we say the derivative of the cost function with respect to W must exist, that implies by the chain rule, the derivative of activation function must exist. That's it. Okay. So that is the reason we actually come up with this table. Quite a while ago, I want you to know the equation of the activation function, but at the same time, also understand the derivative. Because we are going to use it. Right? I'm just going to derive one of it. So, but you can try the other. It's going to use very simple math to derive to calculate the derivative of the log loss function. So that's our log loss function right at the top. So log loss function taking the derivative with respect to a can be represented on the right hand side. Okay. Now I'm giving you that, giving you the results. You can go ahead and verify that. So if y equal to 1, this is binary case, right? So either y equal to 1 or y equal to 0. If y equal to 1, then the derivative will be reduced to AL in denominator and AL times 1 minus AL in the denominator, numerator and denominator. So if you cancel out the term, the common term 1 minus AL, you are left with minus 1 divided by AL. So in that case, you got a negative gradient because AL is always positive. If you're doing negative gradient coming from a bigger value to a smaller value. And if you have y equal to 0, the numerator is AL, and your denominator still AL times 1 minus AL. So you will reduce to 1 minus 1 divided by 1 minus AL. So that's positive gradient. So the two cases really just shows you y equal to 1, you have negative gradient, y equal to 0, you have positive gradient. Okay. Yeah, you can do the rest. Okay, I'm just give you one example. I'm gonna skip this one. It's again just applying very basic calculus. All right, so do this in your own time as an exercise. Okay, I'm going to the heart of the gradient descent, putting all those things together. To go back to the gradient descent algorithm, we try to calculate the gradient on each epoch. And as a matter of fact, we also do it for each layer. So the equation here, we use this the superscript WL to remind us we have to update the weights in each layer for each epoch. Now, how do we actually calculate the gradients? That's the central problem, right? That's where we start to talk about backpropagation. So I want to start by visualizing. What are we talking about in terms of weights and biases? So I'm using again this very simple example. We are going to see this this neural network throughout the explanation. So again, this is 4 neurons in the hidden layer and 1 neuron in the open layer. Now I want you to pay attention here. Why those numbers? Where are we having those numbers? So essentially, we want to calculate, we want to update the weight in the first layer. So there are 4 sets of weights. And W2 has, the destination is 1, so we can use 1 vector to represent all 4 weight vectors. Okay. And B, because we have 4 neurons, so B1 essentially has 4 scalars. And B2, since there's only 1 neuron, there's one scalar. So what are the sizes of the parameters, number of weights that we're dealing with? W1 has 12 parameters. So why 12? Why do we say W1 has 12 parameters? You can pretty much count the number of arrows from all the inputs to the neurons in the first layer, right? Right? Because it's a fully connected neural network. So every input is connected to the neurons in the next layer. So how many inputs do we have? 3, right? How many neurons do we have in the 4? Therefore, it's 12. We have 12 parameters, 12 weight parameters in the first layer, coming from input layer to the hidden. Okay. So you have 4 parameters for B1, which have 4 neurons. So the using the same analogy, W2 has 4 parameters because you have 4 inputs, right? From the hidden layer. You have 1 output layer, so 4 times 1 is equal to 4. And you have 1 bias. So the second layer has total 5 weights. The total number of weights that you need to update, is 21. 16 plus 5. This makes sense, right? I want you to kind of visualize, write down what are those partial derivative gradients that we need to calculate. Okay. The gradient we're talking about is actually in vector, but in this case, it's in the matrix. We have 12 weights. Yeah, go ahead. The bias is 4. We have 4 bias parameters, right? Oh yeah, bias is a number. You can think about bias as a weight. Remember the equation Z equal to W1 times X plus B. Yeah, so bias and weight are both. You can see that all of them are weights, but we just separate. I want you to just think in exactly what we are talking about when we take partial derivative with respect to W1. We are actually taking partial derivative of 12 parameters. Right? We're taking partial derivative with respect to all 12 weights in the first layer. And when we take a gradient with respect to B1, we are talking about all gradients. And for upper layer, there are 4 of them in the gradient for weights and 1 for the bias. So total you have to calculate, update 21 gradient values. Does that make sense? Sure.
Is this what they do for like those really big models like ChatGPT as well, or is it?
But does ChatGPT use this?
Yeah, well, just use gradient descent like this, because I can see why it now takes so much computational power, I guess.
ChatGPT use deep learning neural network, of course. But they don't, they have a similar structure. They have similar structure, but they use more advanced algorithms. But nonetheless, they are much more complicated than this.
I was just curious, it's like, I guess I see why it takes so much computational power now. It's,
Tell me about it, right? You train a lot of models for. Yeah, yeah. HBT, there was a Wall Street Journal article. A reporter, technology reporter, she did a simple calculation. She wants to calculate the equivalent heat or energy needed to have a simple prompt, digital prompt. How does that equate to the energy usage that we have on a daily basis? I think I forgot exactly what kind of experiment he did, but he said something like this, right? If you give reasonable prompt to a check and the amount of computation needed, so they consume a lot of energy, right? And that energy can cook a state of 8 ounces to pretty much to a perfection. So what we're actually saying is we are cooking a lot of steak. And we are sending prompts to check. That's a lot of energy. But anyway, I tend not to think about it because it's mind-boggling how much heat are we creating, right? We're creating so much heat in the data center. So my joke is, all the data center looks like an aquarium. If you look at it, the modern data center, there are pipelines, there are water tank. And all the reason to have that is to what? To cool down the temperature. But I think that's just temporary. That will stay for a while, but I think eventually we have to find a solution from hardware, from the semiconductor sector to really reduce the power consumption by magnitudes of smaller. Otherwise, we are going to produce a lot of green gas effect. All right, so Tim is right. You know, we are looking at this very simple fine neural network. We are already looking at 21 parameters, and 21 is nothing here. There's nothing here. I imagine you have, 100 layers, and each layer has 100 neurons, right? That adds up pretty quickly. Okay, let's put this together. Now we have seen this. Right? We use loss function. We calculate the output based on forward propagation. Then we calculate the loss function, and we started to use back propagation to update the weights by using gradient descent. Now we know the gradient descent. The key for gradient descent is those partial derivatives. Those 21 parameters we need to calculate in order to update the weights. Okay. So essentially for each layer, you need to calculate those 4 vector parameters. You need to calculate what I call it intermediate gradients, meaning they are not the final gradients that we want, but they are necessary. The gradient with respect to your A and the gradient with respect to your Z. Those are the 2 values associated with each neuron, right? And you can come up at the end, the gradient against the weights and the biases. So that's what we are trying to do. All right, so this one, I call this mathematical foundation for back propagation. So bear with me. There's there are only four. Only four. Okay. If you understand this, then you are on your way to understand that propagation. So let's look at it one at a time. So we said we want to calculate intermediate. The first intermediate derivative is gradient is with respect to z. So the first one. So use chain rule. Use chain rule. You can represent this partial derivative at the beginning by replacing it with the derivative of a multiplied by derivative of a with respect to c. Right? That's just chain rule. And what is the term that I circled in orange? What is that one? Because we know the relationship between A and Z, right? Exactly. We will continue to repeat a lot of things that you already know, but we put things together. So it's basically a derivative of the activation function. Do you agree? That term inside the orange circle is simply a derivative of the activation function. So here's the first appearance of the derivative. Why we need to know the derivative of activation function. Because of this f prime. The f prime. Do we say that? I passed the math lecture.
Oh,
No. It's the derivative, right? Okay. Simply because AL and ZL has that relationship. So that's simple. Let's forget about that one for a while. So the second line is about another intermediate partial gradient, right? It's with respect to AL. Now you can also represent that partial derivative with this term that I circled it in green. So another chain rule. So what is the derivative inside that green circle? If you remember the relationship between Z and A, pay attention. This A is from the previous stage. Okay, it's actually the input to the next layer of neurons. This A in the denominator is not the A inside the same neuron. It's actually the output from the previous stage. Okay. Remember, we use A to represent the output for each stage, right? So this AL actually is the input from the previous stage. CL plus 1 is the first calculation in the new layer. So they have this equation, right? CL plus 1 is actually the weight of L plus 1 multiplied by A for the previous stage plus a new bias. So we are getting. So if you take the derivative using this equation, you know the bias is gone, right? Because that's not part of the variable. So you only leave with the term WL plus 1. So the circle, the green circles, represent both the original equation and the results. Okay. Are we okay? This is okay, right? All right. So how do we actually calculate the weight? The gradient that we really want is the gradient with respect to. Now, again, we use chain rule. If you represent the chain rule, I'm using the chain rule to represent partial J, partial W, and come up with a term, the circle in red this time. So what is the partial derivative of Z with respect to W. You look at the equation. You remember how to calculate Z, right? Within each neuron. So if you do that, then you get AL minus 1. The one in the red circle. That's coming from the equation here. Because you take derivative with respect to AL minus 1, WL, you get that constant, right? We're getting there because we are establishing all the results that we want, but we can start to calculate. Okay. So the last one is the easiest one, which is the bias. Again, you use chain rule, separate the term, and what is the derivative of Z versus with respect to B? We know Z and the B has that kind of relationship, right? So the first time after you take the derivative, first thing disappears. So this is pretty much unity, right? 1. This is 1. Agree? This derivative inside the blue box, blue circle is essentially 1. Because of this. This one will disappear when you take the derivative with respect to the bias. Good? All right. Now you have the mathematical foundation. How do we actually put them all together? All right. So here's the key diagram. I'm going to put forward and backward together in one portion. So this part that we have right now is forward propagation. I'm starting to use the orange arrows to indicate the direction of backward propagation. And I'm going to color coded them. All the green derivative on top of boxes are the intermediate gradients you have to calculate. So they are DA2, DZ2, DA1, DZ2. Those are just shorthand notation to represent the gradients of loss function with respect to the activation output and Z. Those are just shorthand notation. Okay. So those are the 4 things. The 4 green equations are what we need to calculate for intermediate gradients. Okay. And the blue derivatives are, or gradients are what we want. And I put them in under 2 boxes because that's when their results can come out. That's when you can actually get the results. So if you look at it, the gradients for W2 and B2 actually come out of after you calculate DA2 and DZ2. That makes sense, right? And also, when do you get DW1, DB1? Only after you calculate DA1 and DZ1. So those are the sequence. Okay. Then the red one are actual calculation, actual equation that make this happen. You started from DA2. And this, because this is what? This is log loss. We actually use log loss first. Okay? And you can calculate DZ2. So 2 reds, those are equations that you want to calculate for those gradients. Those are intermediate gradients. And after that, you can calculate DW2. Because DW2 is simply DZ2 times A1. You already know DZ2 from the previous step. You already know A1, right? DB1 is right here in the forward path. So DW2, you can get it. And DB2 is simply DZ2, so that's kind of a given. So that take care of, so at this stage, your back propagation finished the first stage, first layer. Now we want to go back to the input layer. You continue to calculate intermediate gradient first. So you calculate BA1. And BA1 is based on previous calculated DZ2. So it's kind of the calculation is in sequence, right? You cannot mess up the sequence. You have to do it that way. And DZ1 is simply W2, which is right there, multiplied by DZ2, which is right there. And this is a convolution. Convolution with the derivative of activation function for Z1. And all of them are available. You can calculate.
Where'd the convolution come from?
I'll explain it later. And DW1 is DZ1 times your original input vector. And what's DB1? It's simply DZ1, so that's pretty much consistent. So that's your first encounter of backpropagation using this very simple neural network, just 2 layers. You get 3 layer, simply add 2 more boxes. So the key is you calculate intermediate, those green partial derivative first for each stage. Then you come out with those red derivatives, which are the true calculation. You do it, you finish 1 layer at a time and propagate back toward the input layer. Okay. All right, some implementation issue. How about those numbers such as A2, Z2, W2, B2? Where are they? Right, when you do a calculation, they are needed, right? We already calculated them or used them in the four propagation. And therefore, in the implementation, you need to keep those numbers in your memory. You have to save them. You have to say all those parameters or numbers. So when you do back propagation, you can fetch them back. Question? Does it make sense?
Seems like a lot of steps to remember.
Say again.
Seems like a lot of steps to just remember.
Yeah.
I don't think it'd be like difficult conceptually though to implement it. It just take a while.
Yeah.
You have to do it.
Yeah,
They
it's
should.
just one of those things that takes a lot of operations.
Yeah. This is the easiest way I think I can explain it because of the math involved really is pretty simple. Like, if you think about this, it's a whole bunch of chain. Whole bunch of chain. As long as you know
Very fast.
and essentially, you know, from the beginning, whoever created this algorithm, I think is Professor Jeffrey Hinton. He find a way to make the computation very efficient. But if you look at this, actually, you can see codes already. You can write codes. You can write very efficient code to repeat the process many times, and you get results pretty quickly. So if we summarize that figure and use and list all the essential calculations. What's DZ2? You use DZ2, you can get the DW2, you can get DB1. You calculate DZ1, you get DW1 and DB1. So here's a tricky thing. there's no need to calculate BA2 actually. Um, there's a reason for that, but if you look at it, if you look at those 6 steps, there's no DA2, DA1. Okay. I'm not trying to trick you, but actually, conceptually, that's how you get started. You want to calculate the intermediate partials. At the end, specifically for log loss, there's really no need to calculate DA2. You only need DZ. Okay, this is just n equal to 1, if you pay attention. N equal to 1, meaning one, the data set has only one sample, but with 3 input features. So we are not done just yet. We need to kind of extend it to multiple samples. Multiple samples means that we need to extend the left-hand side to another vector form. Now, there are some interesting variations, right? But if you just look at one at a time, so from left to right, BZ2 doesn't change. It's still the same format. It's just extended to multiple samples. VW2 does have a additional normalization factor because we are talking about multiple samples. EB2 is a little bit tricky. I will explain it together with the evolution later. But here is something that we actually kind of get away from the map representation. We actually start to use NumPy code. This is by necessity because it's really hard to write any mathematical functions to represent that. But just think about it as kind of a variation of that, adding it to multiple samples. And DZ1 doesn't really change that much. And again, DW1 is average over N. DW1 has very similar very similar looking turn as DG1, except for the changes in the parameter. Okay. That is your basis for writing Python codes already. You can actually start to write Python to implement this. Okay, and let me just remind you, what is the cost function? Cost function is actually overall cost function of the sequence. It's the cost function of the individual sample, averaging them over the entire samples, the entire sequence. Okay. So let me see if I have time to explain this. Let me see. I want to give you a summary first. Okay, give you a summary first, so you can start to, yeah. So this is what we will be using to start out our implementation. So next week when we meet again, we will start to introduce Keras as well as NumPy. So I know some of you already know how to use both. Will start from scratch, use Keras as well as NumPy to implement a simple version of the gradient descent algorithm. And after that, you start to use packages, modules. A couple things to emphasize. BZ2 equal to A2 minus 1. BZ2 is essentially, if you look closely, it's actually the prediction error. Is the Y hat minus 1. Why? Because A2 is the output, right? A2 is the output. and y is the original desired output. So EZ2 very interestingly actually represents the prediction error, but without the square. And the error propagates back from the output layer to the hidden layer. So if you recognize DZ2 as the error, and you see DZ2 start being propagated, being used in subsequent calculation. So that's what I mean. That error is propagating back to the next hidden layer. So it actually continue to propagate. Right. So that's just that is actually an intuition here. You have the output and you define the error, right? The error, y minus y hat. It's essentially the cost function. But the cost function after taking derivative actually represents itself in DZ2. And DZ2 is the error, the raw error vector. They start to show up in each stage of the calculation. And the gradient descent is actually performed for every neuron. So we have 21 parameters, 5 neurons and 21 parameters. And this process, if you vectorize it, you don't even have to think about those 21 individually. You just use a vector representation and vector vectorization calculation to very efficiently calculate this. Okay. I'm going to stop right here. Okay. Because the next step is just to implement that 6 steps to get your first experience with implementing gradients. Right. To review the notes, I'm familiar with the whole foundation. Because next week we'll start to do implementation. Okay. Have a good weekend.
So we do the implementation on the collab.
I'll call out contributor.